Okay, thank you very much for being here today. I'm Alberto Massidda. I speak on behalf of SourceSense. Today we'll be talking about machine translation, how we can teach computers to read and write, how we can teach language. We'll be talking about past, so how we did things in the past and how we are doing things today. We will be covering up extensively the old school methods by which the like of Google delivered their first industry-ready machine translation, and how then things changed. And the shift of paradigm was really, really impressive. Everything changed, and nothing is basically backward compatible with what it was once. So that's why it's a dramatic turn of paradigm. So who we are, a brief presentation. We are SourceSense, we are a consulting company, and we focus on open source software. We just use open source software to deliver enterprise-ready solutions. We have been existing for 17 years. We have branches in Milan, Rome, and London. We are experts at open source, DevOps. We build public and private clouds. We also have an edge in data management, like information retrieval, search engines, data crunching, like Spark, and so on, and more things also. We also do system integrations. We are also coders, not only system engineers. Of course, this presentation is open source, and you can really take all these materials and tweak as you want to distribute and do whatever you want. So the outline for today's presentation, we'll be starting with statistical machine translation, how things were done in the past when this field was basically for PhD people, statisticians. There were probability laws, there were fraction counting, marginal probability. I'll try to keep the math as high as possible. We will be running into maybe some formulas, but don't be scared, I'll be really clear about it. Then how things shifted to neural machine translation. Then we'll be talking about three advanced topics, which is domain adaptation, when you want your machine to adopt some style. So for example, you want to talk legalese, or maybe you want to adopt social scientists, politics terms. Then zero-shot translation, which is how we can translate unknown languages, for which we don't have even training data. And then the unsupervised neural machine translation, how we can really get it to work even without human supervision during the training. So statistical machine translation looks at the problem of translating as a ciphering, war, secret messages going from submarines in the German army, and people had to recover the encrypted message in order to save the lives of a lot of soldiers. And the same ideas were implemented to a messaging language which I don't know. It's basically a ciphered message. You know, it's like I turn into something which is unreadable. It's not understandable to me. I cannot consume it. And what if I can recover back the message through probability laws? So this problem is tackled by the foundational work of this was established by Claude Shannon in the theory of information. And it treats the foreign language as a noisy channel. Then we'll be introducing the concept of language model and translation model. So how we can really build a foundation of how language is really turned into. Then how we build the system actually, we train it, and how we use it to decode. So the goal is to translate a sentence in a foreign language, F, to our language, E. This is because it's basically French to English. It's a tradition that our language is E. I will not override this convention in this presentation. So when we have a sentence F, and we have a lot of possible sentences in our language, English, each one has a probability to be the right one for this message we don't know the content about. What is the sentence who gets the maximum probability, argmax? So we take the sentence which maximizes the probability, and that's our sentence. In Bayesian terms, it means what is the sentence that, given the original message, had the best chance to be the one who generated the encrypted message? Is a backward model. So the abstract model is that we transmit E, the original sentence, over a noisy channel. The channel garbles the sentence, and F is received, this message that we don't know. We try to recover E by thinking about how likely is that E was the message, which is the probability that E was said at all. This is the source model. It's something to do with our language. What is the characteristics of our language, our own, which we understand. And then how F is turned into E, which is P, the probability of having the sentence E, given the fact that we observed the sentence F, which is the channel model. It models how things get turned into. So these two models take care of word choice, so we pick the right words, and we reorder them. So PFE cares about words in any order. So it's too late may become è troppo tardi, which is the proper way of saying that in Italian. And but also can be troppo tardi è. So I reversed the order. Doesn't make sense. It looks like Yoda of Star Wars may speak like that. But then we go also, it's too late, which I wrongly can be translated like è troppa birra, it's too much beer. The words are wrong. So this model discriminates the word choice. Then we got this PE that cares about words order. So troppo tardi è or è troppo tardi is the right one for the model, because this model validates the language model if our sentence is likely to appear in our language. So P and PFE, right, but where these numbers, where these probabilities comes from? How do you really calculate that? Well, the language model comes from a machine that assigns scores to sentences. And it estimates the likelihood that a sentence is ever produced. That's my timer. Okay. So if the sentence, how is it going, appears sometimes in a corpus of sentences that I have recorded, like I gathered 1 billion sentences, and how is it going appears 76,000 times. So the probability of how is it going is exactly 76,000 times over 10 to the power of 9, which is that very small number. Okay, it may appear as a very small, so very unlikely, but actually if you think about that, it's recurring a lot of times during our corpus. Instead, the flower, day, medal, of doesn't get any score because it's a sentence that we never ever experience to see in real English. Then we got a translation model. It worries about the probability of a French string given an English string E, how likely is to be turned into that. This is called translation model, and it boils down to computing alignments between source and target language. So the intuition between in computing links between words is actually that the pairs of English and words in other language, like Chinese. I don't know Chinese. I cannot really say anything about Chinese, but everybody here can see that words that come together in a parallel example may be the translation of each other. Do you know what is the meaning of this glyph here? Shrimp, exactly. How do you know that? Because it occurs every time. Also here occurs every time. So this probably is, it may be, it may not be as well, but the chance is really high that that is exact translation. So this is the intuition. We then arm ourselves with training data as much as we can. It's called a parallel corpus. It's a collection of texts. Each one is the translation of the other. So look at that, guarda là, I never see anything like that, and so on. And you can see that that usually can occur with the e, which is the word is in Italian. Then we use an algorithm which is called expectation maximization, and this algorithm iterates over data over and again until convergence. So it stops by itself, and exacerbates latent properties of the system. And it finds a local point of convergence when they say, okay, it's good enough. We do an example with a very, very small corpus. If we have two sentences with 4 symbols, BC translates to XY. Also, B translates to Y. Can you tell me what is the translation of C? X. So C probably aligns with the symbol X, and B aligns with the symbol Y, because we count how many times B appears in correspondence with y, and then we do a marginal count about how many times, and this turns into probabilities. Probability is just 9 out of 10. 90% of probability is just the fact that on 10 observation, 9 times over 10, I saw that. I can see that over 2 times, all my observation is 2 lines, I can see the B twice aligned with Y. And since the probability must sum up to 1, the certain probability, which is certain in this case, that B aligns to Y, leaves us with no other chance that C aligns to X. Now it's time to decode our string, which is encrypted. It's a ciphered message. We can decode that. And by the noisy channel that garbles that. Decoding is basically searching a space, because the word alignments are leveraged to build a space for a search algorithm, translating searching into a space of options. Okay? So once we build our knowledge base on probabilistic, we establish a graph, links between words, and we try to walk this graph following only the promising paths in our graph, which are weighted with our probability laws. So, for example, if we have the foreign sentence, Maria no daba una bofetada alla bruja verde, then we have, in our knowledge base that we've built the alignments, we know that Maria aligns with Mary, because it saw that every time there's a Maria, 100% of times this is Mary. No may align with not, did not, no, or didn't give, but only when no is also with no daba. This aligns with the 2 words. So each one of these options is tagged with a probability that we computed by observing our parallel data. So each one has a probability in it. So when we decode, the algorithm builds the search space as a tree of options. So each time we make a choice, we leave all the choices on our back, and we have new choices with the narrower number of possibilities to explore. It's a tree option which is sorted by the probability that we computed before. Search space is limited to a fixed size, which is named beam, so that we don't get exponential combinations, but we only prune it to a fixed number to keep memory usage low. Each option is picked on a highest probability first. Reordering of words adds a penalty, because the language model penalizes each stage's output. So you basically generate the combinations of words, then you have it to evaluate on language model, which says, okay, these words in this order are okay, but these other words, you actually flip them, so it is not something they observe in usual English. This sentence is unnatural, I'm penalizing it by apply a discount on your probability. Translation stops when all source words are translated or covered. So we start with an empty stack with probability 1, so the maximum possible. Then we explore the options. We may begin by assigning Mary, because it's very high probabilities, 53%, 0.53 is 53%. Then we may try to start with which, but which has a lower probability of being there, so we try to go the direction. We then try to cover Mary did not. We try to fill all those empty spaces, like we play the Hanged Man game, you know? And the more you go, the lesser the probability grows, actually, because you are multiplying numbers under 0, so 0.1 times 0.5 makes 0.05. So the probability is always lesser and lesser and lesser. But if we try to pick up always the highest ranking probability that the language model evaluates at each stage, if you don't make any mistake, it times 1, because it's 100% okay for me. When you end up covering all the space of hyphens, you will have a complete sentence. The translation is over. You can output your thing. So that was how we did things in the past. We did this state of things lasted until 2016, I'd say. Google really, this technique was pioneered in Italy, in Germany, and in Edinburgh. The University of Edinburgh had really, really good scientists. Philip Cohen build this thing. We had the University of Trento in Italy that was a really diamond in this field. But then things change. Then we know what happened. More power, lots of it available. This model is actually very promising, so let's try to experiment with this one. And we got the neural machine translation, which really started kicking in 2016 on. The neural machine translation is based on the probability too, but there's some differences compared to the statistical machine translation. First of all, is an end-to-end system. It's just one system that aligns and translates all together. We don't have two separate, like translation model and the language model that builds two systems that weight the quality, and we have then a third system, which is the decoder, which pulls these two models. We just have one. This is much better because translation model and language model are not trained at the same time, so they are just two systems that we try to make collaborate. We try to build an ensemble, but it's not, they don't share any knowledge, so most of the times they disagree. This process is inefficient. They tend to have different opinions about the same thing, even though they were trained on the same data. Instead, here we have just one system who holds all the knowledge, global, and it's much more efficient. And second, more important, the Markovian assumption instead of naive Bayesian. The theorem of bias established the probability can be of a system of an event occurring can be factored in the single components, because we know that the probability of raining is depends on how much sun, how many clouds, the humidity, the period of the year. Many factors together concur to is it going to rain tomorrow or not. So this, the Bayesian system does a naive assumption that all these factors are independent and makes the problem very tractable, very simple. So we try to examine all different factors separately. But with words, doesn't work really well because words don't move independently. If I'm going to say I am going, am is dependent of the fact that there was an I before. And so you cannot really say that I translate with io and am is sto. Why not sto or sono, which means stay, I'm here. So it does a Markovian assumptions. Each word is hardly linked with the history of everything which precedes. So in mathematical terms, that means there is a sentence f of length n is a sequence of words, w1, w2, w3, wn. The probability of the sentence can be modeled as the probability of having a sequence of words. And it makes this symbol is a productory, is a product of the probability of having a certain words combined, conditioned by the fact, biased by the fact that we observed a full history of words coming before. This is called conditional probability. So how can we fit this in neural networks? How many of people here don't know neural networks? Raise your hand if you don't know what is a neural network. Come on, don't be shy. Come on, come on, come on, come on. Okay. So basically, neural networks is an ensemble of very small units called neurons. These neurons are linked together in batteries, and these links are weighted and determine the strength a neuron can influence its neighbor. If you have a strong influence on the opposite, on the neighbor which are in front of me, by providing an input into these neurons, I will be able to pump them in taking a decision based on which neuron says. And these neurons in turn can influence other neurons until you get to the final stage. And each final neuron is one single class. So if I have a neuron that says this is white or this is black, just one of them will fire up in case I want to say this one or this other. This is a feed-forward network. Basically, when you are training, you feed training data as input, and you compare the output you get to the expected output. The deviation between the expected output is used as a penalization to rebalance all the weights in the network going backward. But a feed-forward network is not suitable to map the temporal dependencies between words, because M has a link to the fact that was preceded by I. And going, of course, as a bound to the IM, which we saw before. So we need an architecture that can explicitly map sequences of words, not all together. This is like stateless, all the input coming together at the same time, and then producing an output because we observed the full truth as an input. We need something which is able to actually take care of evaluating step by step when we see words one by one. And this model exists, is a recurrent network. A recurrent network is just a very simple network in which we have just one neuron. We feed the input one piece at a time, and the network influences itself step by step. But since this way of depicting it is really, really hard to figure out in mind, we prefer to unroll the network times the number of steps that we have. So if we have 10 words, we unroll it 10 times. Each time we feed the network at each time step one different input. So the first will be I, the second will be am, the third one will be going. And each time, at each step, you are not only influenced by the word you are seeing, but also from the history which is as being injected to you at each time step. Please note that the weight we have in all the different time steps is always the same. It's always the same neuron that we copy, and we have it being influenced by all the time steps. This is very good to model, to build a language model, because if we can map the relationship between words, we can then use it to estimate what will be the most probable word that will be generated, given the fact that we saw this history. So we start with an empty state, and starting with an empty token, what is the most probable word that's going to be produced, given the fact that I'm the beginning of the sentence? And it's going to produce a word, W1, which may be and. So this language model thinks that if you are at the beginning of the sentence, you're going to see all the sentences beginning with and. So given the fact that I just begun my sentence, that I saw and, which is right here. I have the laser pointer? Oh, yes. Very sweet. So given the fact that I have seen the beginning of the sentence and I have and, what is the highest probability ranking word that will be produced? The word the, W2, that in this case is here. So given the fact that I saw the and beginning, and how do you map the history? This because this connection. So all of these things are going to influence each step. So if I have how is it going, and I have to estimate how likely is it to be, if I put a special token, which is the end of the sentence, and I put a sentence that I've generated into my neural language model, I can, if I get to see the end token, that validates the fact that sentence is complete and well-formed. Instead, if I see some other word, or my language model try to predict a word which has nothing to do with the sentence I'm trying to fit it means that my sentence is not really that good. So this is a way we build a probability model over just one language that we take as a source. Going to our translation model, the narrow translation model, we rely on an architecture which is called encoder-decoder. The encoder-decoder is an ensemble of two different neural networks that collaborate together, one transforming an input sentence into an intermediate space of knowledge which only the neural network understands, and then this intermediate space is passed as an input to the second network, which uses that knowledge to build the final representation we are seeking. So with a sentence F given made by these tokens and a sentence E, which is our label, that's why we use the Y, we are looking for the sentence E, which maximizes the probability of having a sentence E output, given the fact that we saw the sentence F in a language we don't know. So we want to have the highest probability scoring bag of tokens, sequence of words, not a bag, it's a sequence actually, because the order matters, given the fact that we observed a foreign sentence. This means that at a certain stage, we will be computing the probability of having these next words outputted, given the fact that we have seen this history of words in the target language of outputs, given the fact also that we started with a foreign sentence. This maps everything as a one single sequence in which any certain point of the computation, the next target word in our language that we are outputting has been influenced by the history of the output, but also the history of the input. That's okay, it works, but it's very cumbersome because it means that we have to build just one single recurrent network, which is very complex and very long. Instead, why don't we exploit the fact that we are actually dealing with two different languages that have really no ties, because two different languages don't share vocabulary. They have two different vocabularies. Sorry? Okay. And we separate them in two separate recurrent networks. So we first build with a model based on the input sentence, and we build a vector h. This vector is a summary vector of the source. It represents, in a vectorial form, so a sequence of floating point numbers, how my network judges this sentence. Then we try to output a sequence of words in my language, given the history of what I have put so far. Of course, if I am step number 1, this history will be empty. But more important, given the fact that I observed this state. So when we have a trained network, if we have a network to be trained, I start with random weights, and then I influence my network with the input sentences. And I have this state. Then I'm starting to influence the output network, given the state, the intermediate state. This is how an encoder-decoder network, which is a sequence-to-sequence network, works. So we start, sorry for it's censoring basically my thing. It was the waiter took the place. That was the hidden thing. I curse you, macOS. Which is influencing my network one step at a time. And when it gets to the end, this summary vector, which has witnessed all the tokens, is passed to the G network. The G network starts outputting its first token, given the fact that it has seen all of these things that summarizes all this knowledge, and starts il, which is the. So, and then passes the state, given the fact that I've seen il, and given the fact that I come from here, from this state, which is linked here and pass it here, what am I supposed to generate? Come here, which is the waiter, and then on and on and on and on until you output the last words, and then the network refuses to go further. It just outputs and over. I'm done. Hey, please don't cycle anymore. And that's basically how a narrow machine translation works. And this model was invented in 2014. So all of this is really, really near in time. The problem is with the summary vector is that it constitutes an information bottleneck. Fixed size representation degrades as sentence length increases. This is because the alignment learning operates on many-to-many logic. When we learn, we get the difference between the output and of our network and expected output. We compute a loss, and we propagate that in a backward fashion. The difference is called the gradient that flows backward. The problem is that, what if, for example, I got wrong only this E? Then my output would be different. All the network will be punished just for this one. So I will change the weight also for these bounds. Even the tuk was correctly aligned with prese, and waiter was correctly aligned with cameriere. Just for this error, I will punish the full network. This is not fair. It's really inefficient, actually. So it would be much better if only this one was punished for generating this one. How we can do that? We can put some gates, like in water management, the dams. We put some dams that gate the gradient flow backward through a context vector, which is like a mask of windows that open and close. And it basically constitutes a weighted average of the source states. This is called soft search, also it's called attention model. So what we have here is that instead of passing the full state, we just pass an average sum here. So if I have to generate the word ill, I weight the with 0.7, and all the rest really matters not that much. So the will be the one that will be influencing ill. And if we have to generate camere, waiter is the one that has to weight. All these weights are learned through the process, actually. And so on, and on, and on. And all single words. So if this one gets wrong, when the gradient flows back, it changes all the weights in order to improve the performance of my network. This one will be punished most for saying a stupid thing. This one will get punished, but only proportional to this weight. So the punishment is diminished, and the alignment that correctly predicted these things will actually be kept because it was good. That's okay. Now you know basically everything that needs to be known on the base level to build an error machine translation. What can we do in these final minutes that we've been left? For example, sometimes we want our network to assume a particular style, but we don't have enough. So, for example, I want my network to translate a document using legalese lingo. Have you ever read a contract, one written by notaries, like terms of service? I'm sure you all did. And it's unreadable, but it's actually written in a very specific language. I want to translate legalese documents. You say, well, why don't you just get 100,000 document, you train a machine translation that speaks legalese? I don't have that much data. I have a lot of data instead to train it on common language. So a strategy can be to adapt an array-trained network. First, I train a full network with general data to obtain a general model which is able to translate about everything. Then we train the last layers on new data. So we give the legalese data over the network, but then I keep all these weights fixed. And so all these can change, actually. So these last layers are trained on very few data compared to the bigger training set. And this is the one that changes. The effect is that I transfer most of my learning that occur here. It's inherited here as a starting point, and then is fine-tuned with my trained data, which is much less. This is exploited by one single framework, which is called Modern MT, and I take pride in having been one of the teams that built the first prototype. It's an Italian invention, and we did this in Rome at the P campus. It was and it's all free, open source. You go to Modern MT and you on GitHub and you download the thing and can start translating. Can we do better than this? Of course, those genius folks of Google built a thing which is capable of zero-shot translation. What does it mean? What if we can translate from French to German because we have a lot of examples? We can translate from English to Italian because we have a lot of examples. What if we don't have any training examples, any aligned parallel corpus for English to German? In the past, what we did was to avoid building for 9 language pair 72 models, the combinatorial explosion. We trained 8 models, and then we used English as a pivot language. So, for example, I want to translate from German to Spanish, but I don't have enough data, but I have always a lot of data from and to English. So I trained 2 models, English to German to English, and then the output is sent to another translator, English to Spanish. You can imagine the results. The distortion was so bad that was basically not usable. So most of the times you end up just translating towards English and you read with your knowledge of the English in your mind. Neural machine learning is capable to overcome this. How we do that? Stop before it rings. We send all the data into one single system, but we prepend the token. So when we have to train from French to German, we prepend to German, je suis ici, and then the network is supposed to output ich bin hier. If we're to translate English to Italian, we say towards Italian, I am here, and then sono qui. When we want to send English to German, we say to the I am here. And you know what? The single system will output ich bin hier. What is the magic? The magic is that we sent so many times to the output German, to the output German, then when the network sees a 2D, it prepares itself to output a German sentence. It's like a Pavlovian association. When it sees this, it already knows it has to activate neurons, which relates to German language. It's really fascinating because it really resembles the brain. When you have to switch your brain in forming a sentence already in English, when you have to think in English. And as a side effect, we build an internal shared knowledge representation among between the languages. And this enables to translate between unseen language pairs. So we saw English language, we saw German language, and we can really translate even though we have no parallel data between English to German. That's a very, very big feat. Can we do even better than this? Yes, we can. What if I told you you can train a machine translation without parallel data? Without parallel data. Can we do this? Yes, we can. This is the last frontier, the final frontier. And this was a paper which I saw this autumn, the autumn of 2017. So what we do, we use just two monolingual corpora. So I take Wikipedia in Italian, Wikipedia in English, unrelated articles. I don't need to have a bond between articles. Each corpus builds a latent semantic space. So I build a network that from source sentences is capable to build a latent space in which we have a very compression representation of this sentence. And I can go back to the same or something really similar words. I can generate a noisy representation and then denoise it. This is called an autoencoder. The trick is that similar languages, for example, the English, French, Spanish, Italian, have similar grammars and similar semantic bonds. So they tend to build a similar latent space. And I can map a latent space to another, using an encoder to bring myself into the intermediate space, and using the decoder of the target language to get out of this space and getting out in a different language. So translation now is a geometrical mapping between affine latent semantic spaces. So it's an isomorphism between two spaces which share the same characteristics but have the different objects. And this is it for today. I leave with some links. You can get the slides. It will be published on the website, of course. This stuff that pertains to Google stuff. Also, Amazon built a sequence-to-sequence framework, which is based on MXNet, which is the TensorFlow of Amazon. And this website, which gathers all the material for the very old school stuff, was very fascinating. One last thing, we are hiring at SourceSense, not only DevOps, but I left that because the job was great, but also we hire coders and data scientists. That's it. Thanks for your attention.